Okay, so hopefully you guys clicked on this video because you want to know everything that you need to know about GCSE electricity when it comes to your GCSE physics exam. So we're going to be going through the whole topic. Pretty long, so I'll try and put timestamps in the description below. You can skip around on the video. We are going to be going through the whole topic right from the very beginning to the very end. You don't need to know anything before this, so you can come in with zero knowledge, and hopefully by the end of the video, you'll be totally ready to answer any GCSE electricity questions that you get on your exam. Okay, so let's get straight into it. So the first thing we're going to be looking at is basically how do we represent electrical circuit. So let's start off with a really basic circuit diagram. So I'm just going to draw this, and this might be new to you, or you might have seen something like this before. So essentially what we've got here is a very basic circuit diagram, and I'm going to label the components that we have got. Over here we just have a battery, and over here we have a resistor. Okay, now I've called this a battery. Technically this is actually a cell. A battery is a collection of cells, and here we've just drawn one cell, so this is just a cell. Okay, so this is a very basic circuit diagram that we've got, and in here this would be a perfectly functioning circuit. We've got two components, the cell and the resistor over there, and we'll get into all these components in more detail later. But for now, basically the first thing we want to be able to do is represent circuits. And so these basically these pink lines between the cell and the resistor represent our wires, and they are what carry the electricity. Okay, so we'll go into more detail later, but for now, basically we're going to concentrate on how we represent circuits. And so we need to know a few more symbols that we can use when we draw our circuit diagrams. So the first one that I'm going to look at then, so the first two we've got already is our cell and our resistor. And we also need to know a switch. So I'm going to draw it out for you guys. And this is what we call a switch, okay? And you can have your switch in an open or closed configuration, right? It's a switch. The whole point is if you close it, then basically what you end up with is just a normal regular connection, just like we drew above. It will look like that, right? That's a closed switch. Idea with that is you can have an open switch or a closed switch, depending if you want to connect or you want to basically disconnect. Okay, so that's the switch. The next one we're going to draw then is a lamp. So a lamp is one that might come up in your exams, and it just looks like that. And essentially we've got the wire connecting on either side, and in the middle you've got this X shape. And a lamp is basically just a bulb, right? You can connect it. When you connect it into your circuit, you expect the bulb to light up. The next one we're going to draw is a fuse. So I'll draw over here. And a fuse looks very similar to a resistor, but you've just got a line running through it like that. And a fuse basically just high level what it does. It's essentially very similar to a resistor, but it's rated for a certain amperage. So we'll get on to what amperage is later in this video. But essentially what it means is that this fuse will blow if you have, well, we'll call it too much electricity for now. Okay, so that's what a fuse is. Next thing we're going to look at is a cell. So we already kind of looked at it, but I'll just draw in more detail here. So here you can basically see with the cell, we have a longer side and a shorter side over here. So there's a long line over here is basically the positive terminal of the cell, and the short side is therefore the negative terminal. Okay, so you might need to remember that, but essentially what a cell is basically the source of the what we call the potential difference. And again, we'll get onto that later on in the video, but for now we'll just leave it at that. Okay, so that's a cell. The next one we'll draw then is a voltmeter, and again I'm not going to get into too much detail about what this does, but you might be able to guess it's a voltmeter. It measures volts. Okay, and we'll get into what a volt is. And next to the cell, actually I'm going to draw a battery just to show you guys what that looks like. So like we said before, it's a collection of cells, and so you could draw two cells just like this. Okay, and this is a battery. Perfect. And we're going to move on now to an ammeter, and we'll draw this next to the voltmeter since again they're quite linked together. This one is an ammeter. It measures amps. The next one we're going to look at is a diode. Basically that is what your diode will look like. Okay, so we'll just label that one. That one might be new to some of you guys, so that's a diode. And again, we'll get into what that does later on. Resistor we've already seen. I'm not going to draw it out again. There are some variations of a resistor that you do need to know as well. So the first one that we need to know is a thermistor. And that basically looks like a resistor, but it's got this kind of backwards L shape through the middle. And then we also have a variable resistor. And again, looks very similar to a resistor, but you have this upwards arrow through the middle. And you also have a light dependent resistor. And you might have guessed looks very similar to a resistor, but now we put a circle around it. And we draw some arrows, basically represent the light. And the last one we'll look at is an LED again. So an LED is basically a form of a diode. So what we'll do is we'll just steal the diode over here. Okay, so if I grab that, And we just need to represent that it has some light coming out. So you might have seen LEDs in your home before, and this one is what we call an LED. Okay, perfect. So now basically we've drawn all of these different circuit components. Over here then we have a collection of all the components that you do need to know. You might see circuit diagrams in your exam paper with all these different components, and you just need to know basically what they are. We'll get into more detail what exactly they do later on in this video, but you do need to know all the symbols, you need to be able to recognize them, and you do need to be able to draw them. Okay, so let's test you guys out a little bit. Okay, so go ahead, we've got a circuit symbol here. You guys hopefully should know what this is. And this, of course, is a variable resistor. Okay, so let's write that down. So hopefully everyone got that one. Okay, and next one we've got over here. Hopefully everyone got this one as well. This is a fuse. All right, and the last one that we'll do then, hopefully everyone will get this one over here. And this is, of course, a lamp. So that's circuit symbols. Let's carry on now. The next thing we're going to be looking at then is charge and current. So now we're actually getting into these circuits themselves and how they actually work. So if you look back at our previous circuit, we included over here this cell or this battery. Well, technically this is a cell, so we'll just call it a cell now that we know the difference. So we included this cell in our previous circuit, and essentially what we need to know is that every circuit needs something like this cell to actually work as expected. And what this cell does is it provides something called potential difference. Okay, so this provides potential difference. Okay, so that term potential difference is going to come up a lot again and again and again. So what actually does that mean? Is basically the thing that gives our things in the circuit the push to get them working. Okay, so essentially the potential difference in a closed circuit causes electrical charge to flow. Okay, so over here basically within these wires you're going to have we're going to have basically electrical charge, and it's going to be flowing, and the way that it flows is it gets this push to actually cause it to flow from the cell over here. Okay, so that's the way you want to be thinking about it. So then naturally the next question you might ask is, well, what actually is this charge then? So let's take a look at this in a bit more detail. So this charge basically comes from it's a quality that is part of the electrons in the circuit. So if you think back to your GCSE chemistry, you might remember that you have these metal wires in your circuit. So we'll draw it out like this. And these metal wires are going to be made up of atoms. And within those atoms, you're going to have these electrons over here. Okay, so these are electrons. And so because these atoms are made up of electrons, then essentially the electrons in your metal wire is what has this charge. Okay, so we notice we put this negative sign on all of our electrons. So what does that actually mean? Well, this is the charge. Okay, so all of these electrons have this certain charge on them, and so our cell is basically causing a push to happen, and it pushes these electrons along, and because these electrons are carrying this charge, the cell itself is pushing this charge along the circuit. So the potential difference from your cell causes the electrons to flow and therefore causes the charge to flow. Now this charge can flow at different speeds and rates, and that can vary according to various factors. Okay, so another useful quantity that we might want to measure is not just the total charge, but actually the speed of the charge, or the rate that the charge flows. Okay, so the rate or flow of charge, that's what we call the current. Okay, so we defined our two terms over here. Charge is basically what's on the electrons, and the rate that that charge flows is what we call the current. Okay, so the way to think about this is you might have a bunch of charge over here. So this is all your electrons. They have a bunch of charge, and they are flowing through until they reach sort of this point. And the idea is you can basically draw a line over here, and you can say, okay, well, what is the speed that these electrons or this charge is flowing from over here to over here? Basically, how much charge flows and how long does it take? So you can think of it basically the charge flow per second. Yeah, that's the rate. Okay, and so like we said before, that is what we call the current. And so to work out the current then, we can actually put this in terms of an equation. So the current is equal to the charge flow divided by time. Okay, and hopefully now that kind of makes sense from the way we explained it before. This equation is just naturally what we said in words in the form of an equation. And so you can actually rearrange this equation to get a form that you will find on your equation sheet. And so the charge flow will be equal to the current multiplied by the time. Okay, and on your equation sheet, what that will look like, they'll give you a symbol equation. So the charge flow is a Q, the symbol Q, and that's equal to the current, which is I, multiplied by time, which is a small t. Okay, we'll also put the units on here for you guys. So the charge is measured in coulombs. Okay, so capital C for coulombs. The current is measured in amps or amperage, so we'll give it capital A, and time is measured in seconds. Okay, so you do need to know also the units for each of those quantities, but you do get this equation in your equation sheet. Okay, so now we have an understanding of current in general, and we can also use the fact that in any closed loop, the current is going to be the same throughout the circuit. Okay, so I'm just going to add a resistor over here. So this is basically the same setup that we had above, and the idea is here basically we have one single closed loop, right? The whole circuit is contained within this loop, and we're saying that within this loop, if you were to measure the current at any point in this loop, it would be the same. Okay, the current doesn't change. You can measure it anywhere within a closed loop. The current is always the same. Remember, the current is the rate of flow of charge. Now if we were to change what's in this circuit, so let's say maybe we add another resistor over here, maybe we take that apart and we add another resistor, then you'll get a different current, but still the current at any point you measure it will be the same. Even if you stick something over here to measure it, between the resistors, the current will still be the same in any closed loop. Okay, perfect. So now that we've defined what current is, and we said that the rate of flow of charge or the current basically can change depending on what you have in the circuit. So you can actually now calculate what the actual current will be through any individual component. So we know the current will be the same, but how do we actually work out what that current will be? Okay, so now we can actually take our resistor over here. So actually, let's simplify the circuit again, just so that we're working with a nice simple circuit. And again, we have our cell and our resistor. And we're going to say that this resistor has a resistance of R. And now we're going to introduce something called the, well, we talked about potential difference before, but potential difference we measure in volts. And potential difference we can actually measure across components, okay? So I'm going to show you how we measure it. So you'll basically have a voltmeter like this. And this will give you the potential difference across this component. Potential difference is also sometimes called voltage, and it is measured in volts like we said before. And it's also really important to notice here that we are specifically talking about this component over here. So we're not looking at the whole circuit, we're looking at the current, the resistance, and the potential difference of this component. Okay, so that's why when we measure the potential difference, we measure it across the component. We talk about the resistance of the component, and therefore when we work out the current, we're going to be working out the current through this component. Okay, so that's really important to remember. Now the resistance we kind of talked about a little bit, so I'll just expand on this. This is the resistance, and we measure it in something called ohms, and the symbol for that is, it looks like this. Okay, so this is measured in ohms, and it's basically a feature of any resistor. And you can also say any component basically has some kind of resistance, and that resistance we measure in ohms. So we can give it a number, and that will tell us what the resistance is. Okay, so then we can take an equation to link all of this stuff together, and the equation that we have is that the potential difference is equal to the resistance, or the current, multiplied by the resistance. Okay, so hopefully that looks kind of familiar if you put it in this form where V equals I multiplied by R. Okay, so V, remember, is potential difference, sometimes called voltage. I is your current and R is your resistance. And once again, we can put in our units. So V measured in volts, current measured in amps, and the resistance, like we said, measured in ohms, just like that. Okay, so we have this equation over here, and you can see basically in this scenario, if we wanted to work out what the current was through this component, then because we have the voltage and the resistance across the component, or the potential difference in resistance of the component, then we can basically just rearrange, and I would be equal to V over R. And if we knew both of these numbers, then we could just stick our numbers in. Yeah, so let's have a go then at basically using that equation. So let's draw the circuit again. And this time I'm going to say that this resistance is 5 ohms. Okay, we have a resistor of 5 ohms. And I'm going to tell you that we have a current flowing through the circuit, and that current is of a value of 1 amp. Okay, you have a 1 amp current through this resistor. And remember, I said it's the current flowing through the circuit, right? But because this is a closed loop, it's going to be 1 amp current over here, and it's also going to be 1 amp current through the resistor, and on this side it will still be 1 amp. Remember, the current through a closed loop is the same at any point in the loop. Okay, so now basically I want you to work out what the potential difference across this component will be. And remember, because we're using the value of the resistor and the value of the current through this component, then when we use our equation V equals IR, then basically we just need to remember that what we're working out, that V over here, this potential difference, is a potential difference across this component. Okay, so hopefully that makes sense. So we can just plug in our numbers over here now. We have our current of 1 amp. We have our current of 1 amp multiplied by our resistance of 5 ohms. And so you should get a voltage value or a potential difference value of 5 volts. Okay, so hopefully that will make sense. Okay, so now let's say we keep this potential difference the same. So this reads 5 volts, right? Just like we worked out. But this time I'm going to say I'm going to increase this resistance to 10 ohms. Okay, so now I want you to work out what the new current would be. Right now it's not going to be 1 amp anymore because we changed the circuit. Basically now we've increased the resistance, so we're going to use our equation again. So let's rub this out. So we have our V equals IR equation. This time I want to work out I want to work out the current. So I'm going to write that I equals V over R. And so the current will equal 5 volts over 10 ohms, which should give you a value of 0.5 amps. Okay, so you can see previously we had a current of 1 amp, then we doubled the resistance and we end up halving the current. Okay, so hopefully you can see how that works, and that's the expected behavior you'd get from this equation. Okay, perfect. Let's move on now then. So previously, basically in all of the circuits that we've been looking at, we've had the same kind of setup, and we've been looking at this resistor, and we've given this resistor different values of resistance, right? We said that, okay, it could be a 5 ohm resistor, or it could be maybe a 10 ohm resistor, or 15 ohm, or whatever. But the idea is basically that we've said that this resistor has what we call a fixed resistance, right? So the resistance is constant. Now, if the resistance is constant, we have a special name for this type of component. We call this an ohmic conductor. Okay, so hopefully the conductor part you get, so it's conducting electricity. So any component that conducts electricity, for example, this resistor would be a conductor. And in this case, because the resistance is constant, then we call it an ohmic conductor. Okay, so that's just a special name that we have for it. Now, like we said, okay, so we basically called this an ohmic conductor, and we said it had a constant R. Now, in this case, this component is a resistor itself, right? So this is probably a valid thing to say because resistors are designed to have a constant R, right? So when you buy a resistor from the shop, you're going to be buying a 10 ohm resistor or a 15 ohm resistor, and they're designed to have this constant resistance. So that makes sense to say that it's an ohmic conductor and it has constant resistance. That's fine. However, there are some components, including some different types of resistors, where the resistance is actually not constant. So let's compare a couple of scenarios. So because we said we have an ohmic conductor over here, what that means is that you have a constant R, okay? So constant resistance. So those are basically interchangeable. An ohmic conductor is something that has a constant resistance. So if you look at our previous equation, we had V equals IR. And what we can do is we can rearrange this now to get the R. So the R equals V over I. And basically, because this R over here is constant, right? That means that V over I also has to be constant, right? Because these two are equal to each other. So if you have a constant R, then that means you also have a constant V over I. Okay, so that's fine, but you're probably thinking, okay, that's a pretty abstract concept at this point. So what does this actually mean to us if V over I is constant? Well, one thing we can do to make this a bit clearer is to actually plot a graph. So we can draw our graph of current against potential difference. Okay, so that's what we want. Current on the y-axis, potential difference on the x-axis. So we can draw this graph, but let's go through experimentally essentially how we would get the results to draw a graph like this. Okay, so how do we collect that kind of data? Well, what we can do is we can set up a circuit over here. So again, we're going to have our cell because we need a source of potential difference. I'm then going to have a mystery component over here. Okay, so I'm just going to draw basically maybe something like this. So just something with a question mark to represent that as a mystery component. Not an official circuit diagram, guys, not an official symbol, but we'll just leave it like that for now. And so for now, I'll complete our circuit like this. And the idea is what we're trying to do over here is we're trying to measure the current and change the potential difference across this midstream component. Okay, so first thing we do is, okay, we need to be able to measure both of those. So let's take our potential difference over here. So again, we're working out the potential difference across this component. So we're going to connect our voltmeter just like that, just the same way we connected our voltmeter before. Then we are also trying to measure the current. So how do we measure the current? Well, we use an ammeter. So I'm going to slot in an ammeter in this circuit over here. So our ammeter will look something like this. Perfect. And that's fine. So right now we can get a value for the current from our ammeter, and we can get a value for the potential difference from our voltmeter over here. But then the question is, okay, how do we actually vary that? How do we get a range of measurements? Remember, we want to draw this graph, right? So we need measurements for potential difference across this whole graph, and then we need to plot the corresponding values of current. So how do we get that? Well, the idea is that we want our potential difference to be the independent variable and our current to be the dependent variable. Okay, remember, independent variable, that's the one that you change, and your dependent variable is the one that you measure. Okay, so because we want to change the potential difference across our component, we need to be able to control that. So what we can do instead is basically have a variable resistor set up somewhere else in the circuit. So let's do that. So I'm just going to remove this for now, and we're going to put in our variable resistor. So hopefully everyone remembers the symbol for a variable resistor is basically like that. It looks like a resistor with an arrow through the middle. So let's try and make that a little bit clearer. So then we have a variable resistor, and we're going to hook in an ammeter just like we had before. Okay, remember, we still need the ammeter to measure the current. And remember, because we have a closed loop over here, the current that we measure at this point is going to be the same as the current that is going to be flowing through our component over here, our mystery component. Okay, all right, excellent. So we'll go through the maths of exactly how this works later on, but essentially what we need to know is that when we vary the resistance of our variable resistor over here, that will cause a different value to be dropped across our different value of potential difference to be dropped across our mystery component over here. So the idea is when we increase the resistance of our variable resistor, there will be a decrease in the potential difference in our voltmeter reading across our component over here, and vice versa, right? We can also, I'll use a different color, but we could also decrease the resistance and we'll get an increased potential difference when we do that. Okay, so we can basically play with the variable resistor over here, and when we do that, we can change the value of potential difference through here, and we'll also get then a different reading through our ammeter over here. Okay, so basically, hopefully you can see from the setup, we can get a set of results. So we'll have a results table that will look like voltage over here, current over here. Or you can switch them around, and you might have 5 volts over here, then you drop it to 4 and 3. And basically the way that this voltage will change will depend on what you do to the variable resistor over here, and you'll get a corresponding value for the current from your ammeter. Okay, so that's your very basic method for how you could get different readings for your voltage and your current. To improve this, you could take repeat readings, so you could basically do this setup a few times, and you get a few different values of current for your different potential difference. And you could also, what you could do is remember that your temperature can actually affect your resistance, so you could switch off your circuit between the readings and give the circuit time to cool down, or the component time to cool down, to make sure that the resistance is constant and it doesn't change as you do your experiment. Okay, so that's just a few experimental tips, but ideally basically then you do this experiment, you get a set of results, and then you can go over here and you can draw your results on your curve just like that. So now, like we said, we can draw our current on our y-axis and our potential difference on the x-axis. And because this is an ohmic conductor, this will just look like a straight line. Okay, so we'll get a line like this. And the idea is that if we think what the slope of this line will be, well, hopefully you guys have done this in maths before, but the slope of a line is basically what we call the gradient. And the way you work out the gradient is you work out your difference in your y-axis and you divide that by your difference in your x-axis, okay? And on the y-axis, remember, we had current, and on the x-axis we had potential difference. So basically this translates to I over V. And remember, we said over here V over I is constant, so all we've done over here is flipped it around, right? So the inverse would be I over V, and so this would also be constant, okay? You've just basically done the inverse, and because the first one is constant, the second one is also constant, and so when you draw this on your graph, because your gradient is now I over V, you expect your gradient to be constant, and your gradient, remember, that's the slope of your line. Okay, so hopefully that's quite clear. The gradient is the slope of the line, and that corresponds to I over V. And because it's an ohmic conductor, we know I over V is basically going to be constant because V over I is constant, and therefore we get a constant gradient and we get this straight line. Okay, so this is the graph for an ohmic conductor, and the only thing we need to add over here is that this is at constant temperature. Okay, and the reason why this is important is because temperature can actually affect the resistance. So if we were to drastically increase the temperature, we would get a different resistance, and therefore we wouldn't see an ohmic conductor over here anymore. The conductor would change resistance. Okay, but in this case, we're just going to say that the temperature is constant, therefore we have an ohmic conductor, and therefore we get a straight line on our current potential difference curve. Okay, great. So that's an ohmic conductor. So we can basically do the same kind of analysis for a non-ohmic conductor. You can do a very, very similar experiment for different components which are non-ohmic. So one example of a non-ohmic conductor is, for example, a bulb. And so bulbs are non-ohmic because of the reason that we mentioned basically over here, right? The temperature can affect the resistance. And with a filament lamp or a bulb, basically the temperature does change when you get to very high currents or potential differences. So if we were to do the same thing, right? The same thing that we did above, we draw current against potential difference. And this time actually we'll, instead of drawing the curve like this, we'll draw it with all 4 quadrants, just to show you what happens when the current or potential difference goes to negative. And basically what you'd see is you get a pretty straight line. And then at the end, your line basically curves. Okay, so what's happening over here is that you can see the lamp actually behaves like an ohmic conductor for a lot of the time, right? So all of this section is a straight line, therefore the gradient is constant, therefore your I over V or your V over I is constant, therefore your resistance is constant. Anything with constant resistance is an ohmic conductor. Then we see when you get to very high voltages or very high potential differences, basically over here, even when it's very high and negative, it's still a very large potential difference or a very large current. Basically at this point what happens is the filament lamp starts to heat up. When it heats up, the resistance actually increases, and so you end up basically getting a much less steep line over here. And what's actually going on is that your resistance has changed, and essentially therefore you get a different gradient. Yeah, you can see because you have this curve, you can see the gradient is changing, and at that point then you can say this is now behaving like a non-ohmic conductor. Yeah, because the resistance is no longer constant, it's changing as you change the value of potential difference and current. Okay, so that's one example of a non-ohmic conductor. We can also draw this graph for other non-ohmic conductors. Okay, and again, it's just any component where the resistance is not constant. Okay, so again, we'll draw the current and the potential difference just like that. And just for your reference, guys, this is basically called it's often called an IV characteristic. Okay, so you might hear that referred to in different questions. So that's basically what it's talking about. It's this graph here. When you draw an IV curve like this, that's what we're talking about. Yeah, current and potential difference. So we can also draw this same thing for a diode. So I'll just label this one. This is going to be a diode. And what a diode does, it only allows your current to flow in one direction. Okay, so when you have a positive potential difference, your current will flow. When you have a negative potential difference, your current will not flow. Okay, for example, so you get something like this. Okay, so you can see once you hit a certain positive voltage over here or positive potential difference over here, you get a regular current flow, and actually this looks like an ohmic conductor. Again, it looks like a pretty straight line, but basically what happens is that over here, once you get towards a negative voltage, the current no longer flows, your resistance is no longer constant. You actually get a very, very high resistance if you try to go this way, if you try to have a negative potential difference, and that basically means that the current only flows when the potential difference is positive. Okay, now the potential difference doesn't have to be positive. Basically it just means the diode only allows the current to flow in one direction. So it could be reverse biased. You could have a diode that only allows only allows current to flow when the potential difference is negative, so only allows current to flow in this direction or this direction, right? The whole point is that the diode basically stops the current from flowing in both directions. It only allows it in one direction. Okay, so those are the two IV characteristic curves that you need to know for non-ohmic conductors. One is a lamp, filament lamp, one is a diode. There are another couple of examples of non-ohmic conductors you do need to know. You don't need to know the graphs, but you do need to know that they're non-ohmic. So the first one is thermistors. And again, they are non-ohmic conductors because they have a non-constant resistance. And actually with a thermistor, what happens is when you increase the temperature, the resistance actually decreases, okay? So one application where you might want to use a thermistor is basically when you have a fire alarm. So when the temperature gets very high, the resistance will be very low. So we could draw a circuit like this. We have our thermistor, and again, it's sort of this backwards L shape. And what happens is you might have some kind of circuit where when this temperature gets very high, this resistance will drop very, very low. And therefore, you'll get a very high current flowing through here. And maybe you have some circuitry over here that's triggered by this very high current, and that will cause the fire alarm to go off, okay? And so that's one example that you might have in using a thermistor is in a fire alarm. Okay, the other non-ohmic conductor which you do need to know is a light-dependent resistor. And so again, you could draw this in a circuit. And so I'll just draw the light-dependent resistor for now. So here you have your light-dependent resistor. And for a light-dependent resistor, again, you have a non-constant resistance. What happens is when the light intensity goes down, you have a decreased light intensity, you actually end up with a increased resistance, okay? So again, you can use this in different components. For example, this could be connected to a lamp in a different part of the circuit. And when the resistance in one part of the circuit is really high, more current will flow through the other part of the circuit, okay? So maybe this is basically branched. So you might have a lamp through here. And so you can imagine when you have a lower light intensity, this resistance goes up and this lamp then therefore would be affected, right? So either it would switch on when the light intensity decreases or switches off when the light intensity increases or decreases, sorry. And you can basically change the setup of the circuit to affect what happens to this bulb over here when you include this light dependent resistor. Okay, so throughout this piece, we've been looking at a few different types of circuits, but we haven't actually formally introduced the different types of circuits, right? So here we've got one type of circuit, and over here, then we see the way we connect this voltmeter is slightly different, right? So these two should hopefully look different. So let's actually formally define these now, and you might have come across these terms before, but we have one type of circuit which is called a series circuit, and a series circuit is basically where you have one branch, okay? They're the most basic form of circuit we've already seen before, and you have the components one after the other in a series, and so it would basically look like this, right? You have component number one, then component number two, and then component number three, and it's all one after the other in a line. And with a series circuit, basically we can remember the current through each component is the same. So the current over here, we're going to call I1, that'll be the same as this, and the same over here, and the same over here, right? It's I1 all throughout, okay? That current is always the same throughout this whole series circuit. And the next thing we need to remember is that the potential difference of the power supply is shared between the components, okay? So if we had a total potential difference of 10 volts from our power supply, so this could be a battery or a cell, it's supplying 10 volts to this whole circuit, right? So the total potential difference across all of these components is going to add up to 10 volts. So you might have 3 volts over here, and then 3 volts over here gives you 6 volts, which means there has to be 4 volts over here, okay? Because these need to add up to 10. So the potential difference is split between all of these different components. Okay, so that's the current and the potential difference. And the last thing we need to remember or talk about is the resistance. So these could have several different resistances, R1, R2, and R3. And if you want to talk about the total resistance through the circuit, so we'll call that RT, that would just be equal to R1 plus R2 plus R3, okay? And you could add as many components as you want. The idea is the total resistance is just the sum of the individual resistances. Really nice and simple, you just add them together, yeah? So if you want to work out the total resistance of the circuit, add up the resistance of all the individual components. Perfect, so that's series circuits. Hopefully that's relatively simple, and we've seen plenty of those already. Then the slightly more interesting or rarer example that we don't come across as much is parallel circuits. So with a parallel circuit, basically you just have branches within the circuit. That's all that means. So we've already kind of seen examples of this before because we set up our voltmeter always in parallel. So remember when we did our resistance over here, we also had a branch over here, which was our voltmeter, okay? But this doesn't necessarily have to be a voltmeter, and parallel circuits are basically anywhere where you have a branch, right? So you could have a branch like this, and then another branch over here. And the idea is the components are not connected one after the other, and you have different options for the electricity to flow, right? So the electricity could flow through this branch, could flow through this one, or could flow through this one, right? There's different options, right? The electricity or the current can flow through the different branches. And so again, let's look at this in terms of the potential difference first of all. So let's say we have 10 volts of potential difference over here. That's the source potential difference from a power supply, and that means you're going to have 10 volts through each of these branches over here. So all of these are going to also have 10 volts through them, okay? So the potential difference through each of the branches is going to be the same. And in this case, because you only have one component in each branch, the potential difference is going to be the same across all of these components. Then you kind of have the opposite of that when you look at the current. So the current over here, you might start off with 10 amps of current. And because you have different branches, actually, the total current is split between each of these, okay? So essentially, you might have 4 amps of current through here, then 3 amps of current through here, and that will leave you with 3 amps of current through the bottom branch, right? So all of these basically add up to the start, right? So at the beginning, you started off with 10 amps. It branched off into the different currents over here, but over here, when they all add up again, you're going to have, they're all going to flow back into this part of the circuit, and it's going to add up to 10 amps, but you can see it was split between them in the different branches. Okay, so that's the current in a parallel circuit. And so the last thing we need to look at then is resistance. So when you set up resistors in parallel, that might look something like this. And the idea is that these individual resistances will have R1 and R2, right? So you have different resistances for each component. And the idea here is we're not going to have an exact formula that we need to know to work out the total resistance, or if we were to combine both of these, but the total resistance would be less than the sum of, well, it would basically be less than the smallest resistance, okay? So in this case, if we say R2 is smaller than R1, so R2 is the smallest resistance, then RT would be smaller than R2 as well, okay? So it would be smaller than R2, which is smaller than R1, right? And so let's just put some numbers on to make this a little bit clearer what we're actually saying. Well, we have a resistor over here and a resistor over here. And so we're going to say this one is 5 ohms and this one is 10 ohms. So here we've actually flipped it, where R1 is the smaller one, right? And basically we're saying that RT, or the total resistance, if we were to combine both of these, is going to be less than that 5 ohms, okay? And if this was 15 ohms, and this was 25 ohms, then the smallest resistor is 15 ohms, and so the RT would be less than 15 ohms, okay? So that's basically all we're saying. When you have resistors connected up in parallel, the total resistance is actually less than the smallest resistor in that parallel connection. And the way we explain this is basically that you're given the current more options to flow, or more branches to flow through, so the resistance is actually decreased, right? So because the current has the option to flow through here, or the option to flow through here, and it's got more than one option, it's got multiple options, you could even add more branches over here if you wanted to, and because you're given the current all these options, then the total resistance is actually less than any individual one resistor, okay? Okay, so let's test out how much of that you can apply then. We covered series and parallel circuits, so hopefully we should be able to do some questions now. So we have an example over here where we have a circuit set up like this. We have 9 volts on this voltmeter, we have 4 volts on this voltmeter, and we want to work out what the reading on V1 of this voltmeter would be. So what do you guys think that would be? So very simply, we should know that when we have a series circuit like this, then the total potential difference of our power supply would be equal to the sum of the individual potential differences across all of our components. So we just add both of these up, the 9 and the 4, and we should get the total is going to be 13 volts. So we know that there had to be 13 volts produced by the power supply in terms of the potential difference in this series circuit. Excellent. Okay, let's try another one. Okay, so in this question, we're given, again, another circuit over here. We've got 12 volts from the power supply. We've got 0.1 amps through this ammeter over here. We've got an on-and-on resistance R, a resistance at 30 ohms over here, an open switch over here, and we have a 42.5 ohm resistor here. And we're going to ask basically what is the voltage across this 45 ohm resistor, or what is the potential difference across this 45 ohm resistor. So how would you work this one out? So hopefully, actually, even though it looks quite complicated, you guys all saw it's relatively simple, and all you have to do is basically use your equation V equals I multiplied by R, and in this case you're trying to work out the potential difference across this component. So you want to use the resistance of this component, and you want to use the current through this component. Okay, so you just need to work out what the current through this component is, and you've got the current actually over here, right? And because this is the series circuit, remember the current in any closed loop is going to be the same throughout. Series circuit current is the same throughout all of the components and the whole circuit, so this will also be 0.1 amps. All you have to do is do 45 ohms times by 0.1 amps to get your answer of 4.5 volts. Okay, and final test question then. This time we have a parallel circuit, and we've got several ammeters set up, A1, A2, A3, and A4. And the idea is that we've got the values for A3 and A4. We know what the current through those are. We know what the ammeter readings will be. And so we want to know what is the value for A1 and what is the value for A4. So go ahead, have a go. So hopefully it again should be fairly simple if you just remember your rules in parallel circuit. So in a parallel circuit, remember the current is going to be split between the branches. And so your current will start off over here. It'll be split over here, and then it will flow back over here, and both of those branches will basically rejoin. And what you do then need to know is basically the total current will be equal to the current in those separate branches. And at the beginning and at the end, when the current rejoins and it's the same, then you'll just basically add those two together. Okay, so you're going to have 5 amps at the beginning, and it's split into 2 and 3. And when they rejoin, you're going to have 5 amps again. Okay, so hopefully fairly clear. Through A4 is going to be 5 amps, and through A1 is also going to be 5 amps. Okay. Okay, so far we've basically looked at circuits on quite a small scale. We've looked at individual cells and lamps and things like that. That the type of thing you can basically set up in your lab. So we also do want to consider the kind of electricity that we use at home every day when we plug things in at home. And so that's basically what we call mains electricity. Okay, so this is the stuff that basically comes out your electrical sockets at home. When you plug in your laptop, your computers, your TV, you're basically plugging into the mains electricity supply. And so this type of electricity is different to the battery supplied electricity we've looked at so far. Remember, in all of these circuits, we've been working with batteries basically the whole time, right? Batteries, that's a battery, or individual cells, right? So mains electricity is a little bit different. And one of the key differences is that mains electricity is what we call an AC supply rather than a DC supply, right? So basically all of these are DC, that's DC, that's DC. Anything that comes out of battery or cell is DC, and mains is AC. So what's the difference between them then, right? So AC basically stands for alternating current, and DC stands therefore for direct current. And so the way we can think about this is basically when you have alternating current, it means that the polarity of your current actually changes. So the easiest way to actually show this is with a curve over here. So this will basically be time, and over here you'll have your current. And essentially what's happening is the polarity of your current is actually changing. And so what that would look like is it would go from negative to positive, right? And so you end up with a curve that looks like this. So very similar to a wave, right? So you have the current at some stages is positive, then some other stages is negative. And it basically, that's what happens, right? It keeps switching between the two. Whereas with direct current, basically, you might just get something where the polarity stays the same the whole time. So it might just look like that, right? You just have a kind of positive current the whole time. Okay, so that's what basically your battery supply would look like, the green line there. So looking back at our mains AC supply then, which is the pink line, basically looks very similar to a wave, and we can use some of the qualities of waves that you might have looked at when you did your waves topics in school or in class. And basically, just like a wave, basically we can give this a frequency. So this has a frequency, and with mains electricity, actually that frequency is 50 hertz. Okay, so every time that it comes out of your plug at home, when you plug it in, it has a frequency, and that frequency is going to be 50 hertz. And we can also say that the voltage is about 230 volts. Okay, so those are two kind of factors or two qualities about mains electricity you need to know, and the frequency should make sense when you remember that it's AC. Okay, so that is our mains electricity supply. So now let's actually have a look at how we would connect an appliance to our mains electricity supply. So we have a diagram over here of the inside of a plug, and basically this plug, once you're inside the plug, it basically takes this cable over here and it splits it into the three different types of wire that we've got in here. So this is what we call a 3-core cable, and you can see basically the three different cores. You've got the blue one, you got this green and yellow striped one, and then you got this brown one basically over here. Okay, so that's the 3 cores of our cable, and this is what all your basically UK plugs are going to be made of. Okay, so these three different wires are different colors because they do different things. So let's go ahead and actually label all of these. So the first one we can look at is the live wire. So this is the brown wire over here. And the live wire is brown, and basically what this does is it carries the alternating potential difference. So remember, because we have our alternating current, this means that we do also get an alternating potential difference, right, within our mains electricity supply. And the idea with this live wire is this is what actually carries that electricity supply to our appliance. And even if you have a switch in your circuit open later on, this live wire could still carry voltage or potential difference. So it could still be very, very dangerous. So you never actually want to touch this live wire. Okay, so this one here, that's something that you do need to know. The next one we can look at then is the neutral wire. So that's this blue one over here. So the neutral wire is blue, and what this does is it completes the circuit. So this is the part of the connection that goes from the appliance back to the main supply. Okay, so you would expect this to be close to 0 volts. Okay, so 0 volts or very, very close to 0 volts. Okay, all it's doing is basically completing the circuit. So all your potential difference should be dropped across the appliance, and then when it comes back, it should basically be 0 volts to complete that circuit. Okay, the last wire then is this wire over here, and this is what we call the earth wire. So this is the green and yellow stripes, and the earth wire basically is a safety wire. Okay, so the actual circuit itself can work completely fine without this earth wire. All you need is a live wire and then the neutral wire to complete the circuit. But what the earth wire does is it's a safety mechanism to stop electricity going into your appliance casing itself. So you'll connect the earth wire to your appliance casing, and if that appliance casing ever becomes live, then instead of leaving that electrical charge in your casing, the earth wire will basically make sure that that charge actually goes back to the mains as well. Okay, and so the idea is this should be 0 volts. So it should always be 0 volts unless there's a fault. Okay, so if there's a fault, that would cause the casing to be charged, and therefore that's when your earth wire kicks in, that safety mechanism, and it basically takes away that electricity from the casing and make sure that even if there's a fault, you're still not going to get a nasty electric shock. Okay, so normally there should be 0 volts. If there's a fault, that means there might be actually more than 0 volts transported in this earth wire. Okay, so that's your 3-core cable. Those are the 3 different wires. That's what they do. You got a couple other components over here. So this is basically a fuse over here, and the point of that is basically to make sure your current never gets too hot, or never gets too high, sorry. If your current gets too high, it basically makes this fuse too hot and this melts. And again, it acts as a safety mechanism. If the fuse melts, the circuit will break and you're not going to transport any more current, which is what you want basically if there's some kind of fault and that becomes dangerous to do. The other one that I think they've labeled is just basically the thing that keeps the cable down. But those are the main things that you need to know. Really, you just need to know about the 3 different wires: the live wire, the earth wire, the neutral wire, and their individual functions. So in a lot of the examples we've seen so far, we're taking electrical energy into our circuit and transferring it to a different type of energy. So usually we have a component which takes our electrical energy and transfer it to something else. So for example, in this circuit, we had a bunch of bulbs or lamps. And so we had our electrical energy coming from our power supply and then being transported or transferred into light energy in our individual lamps over there. Okay, so that's an example of an energy transfer. So we can actually put some numbers to the amount of energy that we transfer, and a lot of the time we're actually interested in the amount of energy transferred per second. Okay, so energy transfer per second is what we call power. So in the context of transferring energy or power across an electrical component, we can actually use a formula to work that out. So the formula is the power is equal to the potential difference multiplied by the current. Okay, and we can write the simple equation that the power P is equal to the potential difference V multiplied by the current I. And you should know the units for these two: potential difference in volts, current in amps. and power we measure in watts, okay? So if we look at back to our example with the bulb, we could have power supply over here, and we have our bulb over here. And what we could do is we could work out the potential difference across this, and let's say that's 5 volts, and we could work out the current, and let's say there's 3 amps of current, and therefore we can work out the power, so the power rating, or the power that's transferred across this bulb, and the power would just be equal to 3 amps multiplied by the 5 volts, okay? Or 5 times 3, 3 times 5 is the same thing, and so you get a total answer of 15 watts of power, okay? Now another form of this equation is that the power is equal to the current squared multiplied by the resistance, okay? So I'll just write this simple equation actually, that P equals I squared multiplied by R. And you don't need to know how to derive this, but it's actually pretty easy to work out. So we'll just stick the units on first. So the only new one here is the resistance, and that's going to be measured in ohms. And this is obviously still in amps, and this is in watts, okay? So again, like I said, you don't need to know the derivation, but it's pretty simple. And as long as you know how to substitute one equation to the other, essentially what you do is you take your P equals VI equation, or more commonly it's written as P equals IV, so let's write it like that. And then you take that and you use your V equals IR equation, and basically you got equation 1, equation 2, and you sub one into the other, and if you do that, you'll get P equals I squared R. So I'll leave that for you guys to have a go at in the comments to finish that one off, to see the derivation, but you don't really need to know it for your exam. This is just another form of that equation, but if you know the derivation, you can see where that comes from. Okay, perfect. So now we can actually look at the energy transfers in the context of appliances we have at home. So here we've just looked at a lamp. So that's one example, but we can also look at different appliances. So we said already that energy transferred equals power multiplied by time. Okay, so that's basically what we've written over here. The energy transfer per second equals power, and therefore energy transferred not per second is just the power multiplied by the actual time, right? If you want to work out the total energy transfer, you just multiply the power by the time. And so naturally this gives us the conclusion that if you increase the power through an appliance, or you increase the amount of time you have the appliance switched on for, then the total energy transferred on that appliance is going to be higher, okay? So the higher that power rating and the longer you switch it on for, you're going to end up with more energy being transferred. And so a lot of the time you see a measure of this with the term watt hour, okay? So far we looked at energy, and essentially the normal unit for energy is joules, but you can actually have this alternate unit which is called watt hours. And hopefully you can see where this comes from now, right? So this power over here is going to be measured in watts, and you multiply it by this time over here, which can be measured in hours. And when you do that, you can get the energy transfer, or the energy basically that's transferred through an appliance in this term watt hours, okay? So sometimes you might see that in an exam. That's basically what's happening there. It's just alternate units being used here in your energy transfer equation. And so for example, if you had 20 watts being transferred for 2 hours, that will give you a total energy transferred of 40 watt hours, okay? A lot of the time this might be in kilowatts, but then you just might get the final answer in kilowatt hours, yeah, something like that. And hopefully this is not too confusing. It's just another expression of energy being transferred. All that's different is you just have a different set of units over here, okay? That's all it is. So 2 examples that you do need to know about when it comes to energy transferred from basically a mains electricity supply is we've already seen the bulb, but instead of having the bulb, you could instead have your mains electricity supply, which will draw like this. So this is an AC supply, and you could connect it to a motor instead, okay? So I'll just draw a big M for motor. And the idea here is, again, as usual, as you might expect, you're going to have electricity being supplied, and then you're going to get out kinetic energy over here, okay? So that's the energy transfer. That electricity is transferred to kinetic energy to cause that motor to move, yeah? So movement energy. Yeah, so you have electrical to kinetic. You can look at a similar example over here. So again, let's stick with our mains electricity supply. But instead over here, you have a heating element. So I'm just going to represent this with a resistor for now. But this would be any kind of heating element, okay? So for example, a toaster, or you might have hair straighteners, something like that. And the idea is, again, you've got your electricity supply and you're transferring it to this time heat energy, yeah? So this time you're getting out heat or thermal energy. So that's your energy transfer over here. Okay, so two examples that you need to be aware of. One, we're transferring electrical energy to kinetic energy, and one where we transfer electrical energy to thermal energy or heat energy when you try to heat something up in some kind of heating element. Okay, now those are examples of energy transfers you might see in typical everyday appliances at home. And actually, when you look at your appliances at home, they might have something called a power rating. And basically what that is telling you is how much power that those appliances are rated to use. Okay, so the higher the power, that means the more energy it's transferring per second. So if you have a really high power toaster, for example, basically you're transferring more energy per second, and so you can transfer more of that heat energy in a shorter amount of time, right? And so your toast might be done a lot quicker if you have a higher power rated toaster, for example. And like we said before, if you wanted to actually calculate that, then you could use your equation P equals IV again, right? So if you had the power rating, you could work out the current or the voltage depending on what quantities you have, okay? And the last thing we'll look at here is this term work done. So another way to say that energy is being transferred is that work is being done, okay? So those two are basically interchangeable. And for electricity, we can say that work is done whenever charge flows in the circuit. So whenever you have a charge flow in your circuit, i.e. you close your circuit, that means that work is being done, okay? So remember, the reason we can say that is that in our circuit, we had these tiny electrons with all the charge. And when we close the circuit and the electrons are able to flow through the circuit with their charge, that's when work is being done, right? So the electrons, when they flow through, they can transfer some of their energy and actually cause work to be done. And so here, we're actually looking in terms of charge instead. So we can actually have another formula of our equation for energy transfer. So energy transferred is equal to the charge multiplied by the potential difference, okay? And the charge, where does the charge come from? Well, it comes from these electrons, just like we mentioned before, right? So we can write these in symbols. E, energy transferred, equals Q, the charge, multiplied by V, the potential difference. And Q, I don't think we've covered before, but Q is the charge, and that's measured in coulombs, okay? And hopefully the other ones you should be aware of. So energy is going to be in joules, and your potential difference is going to be in volts. Okay, perfect. So this section really is hopefully relatively simple in terms of the theory. Really what it is a lot of equations that you need to be able to apply. So let's have a go at applying some of these equations. Okay, so a couple questions then to test what we've just gone through. So the first one here is the power output of a motor is 1.5 kilowatts. Calculate the time taken for the motor to transfer 450,000 joules of energy. So let's have a go at this one. So we basically want to use the fact of what we know about power transfer and energy. So the equation that links those together is that the energy transferred is going to be equal to the power multiplied by the time. And so if we know the power was 1.5 kilowatts, and we know that the energy transferred was 450,000 joules, just write kilojoules for short, and we can put time over here. So to rearrange then for time will be equal to 450,000 divided by 1.5 kilowatts. And so we just need to remember here to transfer that 1.5 kilowatts to watts, right? So it should be 1,500 watts. So that's what we should write. And then you can work out what T you get over here. And if you put that into your calculator, you should get 300, and the unit will be seconds, okay? So that's the first one, hopefully fairly simple. Second one then, the power output of a coffee machine is 2.53 kilowatts. The mains potential difference is 230 volts. Calculate the current in the coffee machine. So this time we're looking at the current, looking for something slightly different. So the power output we know is 2.53 kilowatts. So this time basically we need to identify what equation to use, and we're going to actually use the P equals IV equation over here. The reason being, we're given the voltage in the question and we want to work out the current, and also given the power, okay? So we can just rearrange here. We want to work out the current, so let's rearrange for current. Current will be equal to the power divided by the potential difference. And so now it's just a case of plugging our numbers in. So we had 2.53 kilowatts of power, so let's transfer that into 2,530 watts divided by our potential difference of 230. And if you plug that into your calculator, you should get an answer of 11. And the unit, remember, working out the current, the unit would be amps over here. So you have 11 amps of current in the coffee machine. So again, hopefully fairly simple once you understand what equation to use. So we've talked about mains electricity now, and in the UK we actually have a system in place to transport mains electricity and to get this main supply into your house to consumers for domestic uses. Okay, so to actually transfer that electricity, we need a system of cables to take it from our power station into our homes, and we also need something called transformers. Okay, so let's actually start to draw this out. So first of all, let's define what a transformer is, because we mentioned that. So a transformer is basically something where it can increase or decrease the potential difference of our electricity supply, right? So you could have a transformer that increases the potential difference, or you could have a transformer that decreases the potential difference. And the way that works is you have an input supply over here, an input electricity supply. You then have your transformer over here. And when it comes out the other end, the electricity supply is basically being transformed, okay? So you have an output over here, and this might have a much higher potential difference if this was lower, or vice versa, right? This could be higher and then it is being lowered on this side. Okay, so that's basically all it does. Very simple, very high level. That's what the transformer does. It transforms our electricity supply into something with a higher potential difference or low potential difference. Okay, so there's two types: one that steps it up to a higher potential difference, that's called a step up transformer, and one that steps it down to a lower potential difference, that's called a step down transformer. Okay, so now let's apply this to our mains electricity supply. So we had this problem, right, where we had our power station over here, and basically we need to figure out a way to transport from our power station all the way to our homes, right? Our power station could be really far away from our homes, so we actually want to use the electricity. So how do we transport it across? So the idea is, what happens is you have your power station, this then outputs some power into your transformer, and over here what you have is a step up transformer. So remember, we talked about the difference. The step up transformer basically increases the potential difference, and as a byproduct, when you increase the potential difference, you end up decreasing the current. Okay, so what comes out over here is your output, and you have a really high potential difference and a really low current. And so then these are basically taken to these transmission cables, and these transmission cables carry these to very far distances. Okay, and that's the key here, is because these power stations could be very far away from your towns or your cities. These transmission cables have to carry this power a really long distance, and so if you had a much lower power potential difference and a much higher current, you would end up losing a lot of this energy as heat. So what this means is, because you have this low current, you lose less energy to heat. Okay, so there's less energy wasted through these transmission cables when you have a lower current, because it produces less heat. Okay, so that's the whole reason we have this step up transformer. We need to transport this through these really long transmission cables. We don't want it to get too hot, because you're going to lose lots of energy as heat like that. So we have a really high voltage and a really low current when we transport it through these transmission cables. And so it makes our whole process here much more efficient. Okay, so this basically, we can say this increases the efficiency of transporting our electricity supply. Okay, perfect. Now we get to this point over here where we might have some houses over here, and that's great, but remember, we have a really high potential difference and current. So before we actually get to our houses, we don't want to transport straight into our houses. There's a really high potential difference electricity supply, because that's too high, it's dangerous, and it's not really useful for us to have an electricity supply with that high of a voltage. So instead we have over here a step down transformer. Okay, so that basically does the opposite of our step up transformer. This now decreases the potential difference instead. And remember, because it decreases potential difference, as a byproduct, we also end up increasing the current. Okay, so it decreases the potential difference to a usable potential difference for our domestic use inside of our homes. And that means we have a much more useful form of energy, and we don't have this really high potential difference electricity going to our homes, which could be quite dangerous. Okay, so this whole network of the power station, the transmission cables, and the step up and step down transformer, this section basically in the middle, this is what we call the national grid. Okay, so everything from the power station up to your house is what we call the national grid, and it's this network of transformers and cables essentially, which is used to transport our electricity from our power stations into our houses or businesses or whatever. Okay, so hopefully that will make sense. Okay, so if you're doing these separate sciences, so sometimes it's called triple science, basically there is one more topic that you do need to know, and that is called static electricity. Okay, so this is again only for those students doing separate sciences. So now, before we were working with wires and things like that, but now instead we're going to be looking at the insulating materials instead. So before where we had conductors, now we have insulating materials, and insulating materials basically are the opposite of conductors, right? They don't allow electricity to flow. Good electrical insulators are where it's difficult for electricity to flow. So basically, with static electricity, what we do is we take two insulating materials and we rub them together. So for example, let's take these two rods. And we're going to say these are both two plastic rods. And we take them, and because they're both insulating materials, we rub them together, okay? And what happens is because these rods, again, they're made up of these electrons. So even though these are insulating materials, they're still made up of atoms, and those atoms are still going to be made up of these electrons, right? And so what happens when you rub them together is you end up getting some of these electrons jumping from one material to the other, right? So you get some electrons jumping from this one to this one, and you get this transfer of electrons, okay? So electrons transfer, and on one material you're going to get a gain of electrons. So when you increase the electrons on a material, you end up getting a negative charge, okay? And the reason for that is because the electrons themselves obviously have a negative charge. Usually the material is going to be neutrally charged because the charge that it has in its electrons is balanced out by the charge that it has in its protons. But in this case, because you transferred extra negative charge to it, now overall it has a negative charge. And the material where it lost electrons, basically some of the electrons jumped over here to this one, right? So this rod basically lost electrons. That means that over here you're going to get a positive charge, right? So now you have, because you've lost some of your negative charge, you're left with extra positive charge that's not being balanced out by those electrons because those electrons are no longer there. Now the key thing is when you stop rubbing these together, because these are insulators, that charge is not going to be able to flow anywhere, and you end up with this static charge, okay? So if you have your rod now, this one is going to be positive, this one is going to be negative, and the idea is that charge is basically trapped, okay? It's statically charged. This one's got an excess of electrons, this one's got slightly less electrons, and basically that charge can't go anywhere. So now we have two charged objects, okay? And let's imagine we did this with a bunch of objects. So let's put a couple more over here. So this one we're going to say is also positive, and this one over here we'll say is negative. And it's the same reason, right? We did the same thing. We just rubbed them together and we caused the buildup of charge on both of these materials as well. And so now because these are charged, right, we can put these symbols on them. So positive and negative, and this one's positive and this one's negative. And we should hopefully know basically that when you have charged objects and you bring them together, you get some forces between them, right? So very similar to maybe what you've seen before. So if you were to take a positively charged object and another positively charged object, what would happen is you'd have these force of repulsion between these two, okay? So the like charges will repel, and if you instead have two opposite charges, so you have a positive charge and a negative charge, then these will attract, okay? So if you ever heard of the saying opposites attract, that's exactly the thing that's going on here. When you have two like forces, they repel each other, and you have two opposite forces, they attract each other. Okay, so this is an example of what we call a non-contact force. And a non-contact force is basically whenever you have a force, and you guessed it, there's no actual contact between the two things which are exerting a force on each other, right? So in this case, you have two like charges brought together. They don't actually touch each other, but you still feel the force. And the same thing when you have two opposite charges, when you bring them together, they're already attracted to each other before you even touch them, right? So there's no actual contact going on. That's why we call it a non-contact force. All right, so as you mentioned, these objects, they have a buildup of charge. And what can happen is if you take these two objects over here where they have opposite charges, then basically because these both have a buildup of charge, then what happens is the electrons can actually jump from one to the other. So let's draw that out over here. So remember, this is positive. This has basically got a lack of electrons. It's basically some of the electrons have gone missing. And this one is negatively charged, so it's got a bunch of extra electrons, right? So what can happen is if you bring these two objects close enough together, without even touching these electrons, basically they're going to be so attracted to this positively charged object over here, the electrons can actually jump over, okay? And when they do that, that's basically when you might see a spark. So if you've seen an electric shock or some electric sparking before, that's something that might be happening, right? You might have two oppositely charged objects, you bring them very close together, and you'll see the spark between them, and that's the electrons literally jumping over even before they're touching, okay? So if you were to do this, where you take, you can take two insulators, you rub them together, you then bring them closer to an oppositely charged object, and you might see the spark, and that's what's going on there, is these electrons basically jumping over. Okay, so there's a couple of observations we see in the sparking. There's this attractive force, there's this repulsion force, these non-contact forces we're seeing. And so we actually do want to be able to explain why we see these observations, okay? And that's where we get into this concept of electric fields. In particular, we're just looking at the concept of fields in general, right? So a field is just an area where you might be under the influence of something, for example, some kind of force, right? So you might have heard of the term force field, right? The idea is whenever you're in this field, you'll feel a certain force on you. Okay, that's basically what's going on. And you can see how this applies over here, because over here, nothing was touching. But if you introduce this idea of fields, well, okay, it kind of makes sense, right? Because if these objects were in a force field or in each other's force field, then it makes sense why they would feel the force without actually touching each other. So from our observations over here, we know that the charged objects must have some kind of electric field that it creates around itself. And we can also see that the closer you are to the charged object, the stronger the field, right? And again, that makes sense, because if you think about it, if you were to take these two and you put them really far away, then you wouldn't really feel this repulsion force. But the closer you push them together, the stronger that force becomes. And the same thing with the attraction. The closer these are together, the stronger that attraction force becomes. And when you push them away from each other, the force of attraction is actually not that strong, right? And you might not feel it once they're far enough away from each other. So basically, we can interpret that as the distance between the objects increases, the force weakens, okay? And so with these, we know there is going to be some kind of field around them, but the fields that we really need to be able to draw is anytime we have a radial field for a charged sphere. And the reason for that is because a lot of the time we actually model things as spheres and charged spheres, and so if we know what the field looks like around a sphere, then we can basically extrapolate that to different models and different objects when we draw them out in diagrams, right? So when we have an object over here, I've given it a positive charge, it's a spherical object, and basically we need to know what the field would look like. And essentially what you end up getting is this radial field, okay? And what that means is if you were to draw the radius in the middle, right, different radiuses or radii, then they will look something like this. And basically when you extend these out past the sphere itself, that's what the field looks like, okay? So you don't need to draw these ones inside, but essentially that's why we call it a radial field. So here we have a radial charge, you have a positive charge, and the field is radial, so it goes straight out at right angles to the edge of the sphere. So you can actually draw a few more on like this. And these are all at right angles to the edge where they meet the circumference of the sphere. Now, one thing to note is the closer these field lines are together, the stronger the field is. And so basically, if you were to basically draw this on, you can see over here when you're quite close to the sphere itself, these field lines are quite close together. And the further out you go, to really express this, let's extend a couple of these out. You can see now that the distance between these field lines is a lot further away. So the larger that distance between the field lines, the weaker the field is, okay? So the closer together, the stronger it is, the larger distance, the weaker it is, okay? And that makes sense. On our observation we saw before, the closer you bring these together, you get stronger attraction or stronger force. And you can see why that would be, because the field gets stronger the closer you move towards this charged sphere, okay? The other thing which we've drawn on over here is these arrows. And basically these arrows, the direction you draw them is the direction that the force would act on a positive object if you were to bring it into this field. So for example, if you were to bring another object over here and it was positively charged, now because this is also positively charged, this would act to repel, right? Because like forces repel, and therefore this positively charged object will be repelled in this direction. So that means that our arrow is drawn in this direction, right? And the same thing, you can take this object over here and you can basically take it wherever you want. If you want to put it over here, you can see again it would be repelled in all different directions, and that's the direction that the arrow is basically pointing in. Okay, so that's how you draw the direction of the arrow. hopefully then you should realize that if instead this was a negatively charged sphere, so let's change the charge over here. We make this negatively charged. Then naturally, if you were to bring a positively charged object into this field, now this would actually be attracted to the field. It wouldn't be repelled. And so now the force would be in this direction. That's the force that would feel. And what you do is you'd have to flip all of these arrows, right? So instead of having the arrow in that direction, you flip it. And so it would be in this direction now, okay? And you do the same with all of these, right? So you'd have to go and change the direction of all of these arrows, which I won't do right now because it'll get a bit messy. But basically that's what you would do. So hopefully that makes sense. The direction of the arrow depends on the direction that a positively charged object would feel a force in that particular direction if you were to bring it into this field. Okay, so that's basically all you need to know about how to draw the field itself. And the last thing we'll do is we'll just look at our sparking example, and you can apply this fields idea to the sparking example that we talked about before. So even though the two objects don't touch, the charged particles still have a field which causes these electrons to feel this force and jump over. Okay, so over here, just like we said, objects itself, they don't actually touch, but there's still a field. And so the electrons, they're in this field, they feel that attractive force, and that's what causes them to jump over. Okay, so that is pretty much it. That's the last topic, that's static electricity. Again, you only need to know this bit if you're doing separate sciences. But overall, that is all of electricity for GCSE Physics, and hopefully that was useful.